Thank you. Thank you. It's good to be here, and I'm delighted to welcome all of you here today. Most of you are from Rutgers, so it's a little funny to welcome you to Rutgers, but I do that anyway. And for those of you that aren't from Rutgers, it's really my pleasure to welcome you here. This first Mid-Atlantic Regional Climate Symposium, I think, is a very important milestone for us here at Rutgers. And to provide some context for this event, perhaps a little history is in order. 2 years ago, a symposium was held here at Rutgers to bring people together from within Rutgers to further our collective scholarship on climate change. And the goal at that time was to pilot our own program with an eye toward eventually expanding it into a regional symposium. Sometimes there's a slip between the cup and the lip, and that year the slip was that Superstorm Sandy hit. And little did we know that Superstorm Sandy would make landfall in New Jersey during the week before that symposium, and that many in the Rutgers community would still be without power on the day of the event. However, the university was open for business that day, and all of you who participated at that point persevered, and all the rest of us that were still waiting to get our electricity back at that time finally got it back. So last year, with many of our neighbors still reeling from devastation of Sandy, it was decided to put the regional symposium on hold. The feeling was that it was only fitting to focus on Sandy and its associated impacts, our experiences from the field, and what climate change implies for future vulnerability of natural and social systems. Yet, as one of the oldest academic institutions in this country, soon to embark on our 250th anniversary, we're known for our long-term perspective, and we never lost sight of the original goal. And therefore, I'm especially pleased to welcome all of you here today, those of you from Rutgers and those of you who are guests from other institutions, for the first Regional Climate Symposium. Rutgers recently launched a strategic plan, and we're just about to have the New Brunswick strategic plan completed. In fact, it is completed, and it's going off to the Board of Governors and Board of Trustees committees today. But in the strategic plan for the university, it emphasizes our commitment to address some of the most pressing issues and problems of the 21st century. Climate change is arguably the most important global environmental issue of the 21st century, with worldwide consequences for people and ecosystems. Rutgers Climate Institute facilitates scholarship, education, and outreach on the important issue by building bridges across departments, schools, and disciplines. And all of you, I'm sure, have been seeing the news. We have beautiful weather today, a little on the chilly side, but it's warming up, I understand, over the next few days. But we've seen pictures of what's happening in Buffalo. I lived in Albany for 8 years and got a lot of snow. I grew up in Iowa. We had a lot of snow, very cold weather. But I don't remember ever being any place, in fact, I'm sure I wasn't any place, that had 5 or more feet of snow at one time. You know, it would pile up in Albany. By the time winter was over, you couldn't see out of your driveway because you'd thrown the snow so high. And it used to be frustrating to me to shovel my one-lane driveway, go back to the garage, get my car back out, only to have the snowplow come by and throw another 3 feet of snow across the driveway I just shoveled out. But the people in Buffalo are really reeling. And I think that the topic of climate change is one that is so critical for our nation. And I think some of our politicians have awakened to that reality, others haven't. And I think all of us here in academia have to keep fighting to make it clear that this is a real issue. It's not something made up, it's a real issue. I hope that you find today's proceedings insightful, but I also encourage you all to keep working together to advance our collective knowledge and to be inspired by the challenges and opportunities inherent in your work. What you do is important. I was a social worker, and I can tell you that issues of climate, like the snowstorm out in Buffalo, Superstorm Sandy here, and I lived, by the way, for 13 years in Chapel Hill, North Carolina, and we had many hurricanes and some associated tornadoes while I was there. All of those things affect people. It's not just land and property. They affect people. They affect people's lives in very critical ways. So the work you do is important. Glad you're here. Hope you enjoy the symposium and look forward to hearing the results. Thank you again for being here.
Well, good morning again. I'm Jim Wright, and I'm from Earth and Planetary Sciences, geology to most of you, but I'm on part of a planning committee, and I'd like to introduce those now. We have Ben Lintner from Environmental Sciences, Pam McElwee and Heidi Hauserman from Human Ecology. Oh, thank you. And Laura Snyder from Geography. I don't know how I was chosen to be the MC. Clearly, I missed a meeting or failed to respond to one of the key emails that Marjorie sent, or this is her retribution for me going into the Witness Protection Program from time to time and not answering her diligent emails. But I am here today. She did dare me to wear a tuxedo. I think it was her way of being clever. I actually just called her on her bluff and pulled out something I haven't worn in 26 years, but and I'm your MC for today. And speaking of Marjorie, she didn't put it in my notes to introduce her, and I think we all should give her a round of applause because today is a success already with the lineup that we have to be presented today. Marjorie is the Associate Director of the Rutgers Climate Institute, and without her, you wouldn't be sitting here today. And let's give her a round of applause. And while there's immediate success with today's program, I think the long-term success will be judged by the collaborations, the friendships, the interactions, possibly even the NSF or other grants that might emanate from conversations that started today. Now, and I'm going to read this because this is what Marjorie provided us. The purpose of this symposium is to stimulate the interaction and collaboration amongst the community of natural and social scientists and researchers, and the students that are here. And we have involved the greater New Jersey area here, inviting people from our suburbs to the north and west, that being New York City and Philadelphia, as well as many other places to the south, Maryland and Delaware. We do welcome colleagues from many universities, and I'll name a few that are on the list: Bryn Mawr, Columbia, Drexel, GFDL, Princeton, the National Weather Service, NJIT, USGS, Raritan Valley Community College, Richard Stockton College, and that university from Pennsylvania. Maybe Ken Miller's the only one who got that reference, Penn State. Another key announcement is at the bottom of your agenda. If you're not from Rutgers, the RCI password or wireless login is RCI November. So if you want to log into our wireless network, you can find that password at the bottom of the page. It is my pleasure at this time to introduce Tony Broccoli. I was introduced to Tony's work in graduate school. Tony was working with Suki Manabe down at GFDL, and I think one of the first papers that we read in our climate change seminar were the Manabe and Broccoli in 1985 and the Broccoli and Manabe in 1987, where he, using the GFDL models, was looking at the influence of orography, ice sheets, and other things on global climate. From there, I followed Tony, and then we both have ended up at Rutgers and have talked many years. Tony, in looking at his CV, I was really impressed with a 1981 paper, which is entitled A Microcomputer-Based Teletype Control System, that was published in the National Weather Digest. But Tony has become an international expert on climate change, and I'm going to hand the podium off to Tony right now.
Thank you very much, Jim. I am feeling a little underdressed this morning. I also have one of those outfits hanging in my closet, but I wouldn't be as confident that it would fit me as well as, Jim, yours fits you. This morning, it's a pleasure to be here because I have the honor of introducing the morning's keynote speaker, Mark Kane, who is the G. Unger Vedelson Professor of Earth and Climate Sciences at Columbia University. Mark is widely known for his accomplishments in the field of climate dynamics. His work on the role of the tropical Pacific Ocean in climate variations has won him honors from the major professional organizations. He's a fellow of the American Meteorological Society, the American Geophysical Union, and the American Association for the Advancement of Science. He has also won two very prestigious honors from these professional institutions, the Sverdrup Gold Medal from the American Meteorological Society and the Maurice Ewing Medal from the American Geophysical Union. In 2013, Mark's scientific accomplishments were recognized by his election to the National Academy of Sciences. It's my pleasure now to introduce Mark, who will address the keynote question for this morning: what can we say about the climate of this decade? Mark?
Oh, good. I don't have to put my glasses on.
Here you go. And
Thanks.
then there it is. And this should be. We should
Get his quotes about the
I did. I rolled it.
Good. Okay. Well, if I were braver, I would give this talk instead. But although I do a lot of predictions, I'm older now, and I'm trying to gain knowledge. So this is a quote from Lao Tzu: "Those who have knowledge do not predict, and those who predict do not have knowledge." So let's talk about what we can say about the climate of now. And now is not normal. If we look at ongoing issues for over the decade or so, there's a persistent drought in California and the Southwest. There's a drought in East Africa, and there's been this pause or hiatus in global warming over the first decade of the 21st century. And if you remember last winter, it was cold. Okay, it was very cold here. It was warm in Alaska. There was also record flooding or record rainfall in Great Britain. And so and of course right now there's this colossal snowstorm in Buffalo. Okay, this picture that I've been using as background is from the Carteret Islands in New Guinea. One of these is the Whoops, no, that's not good. Okay. this from the Carteret Islands in New Guinea, and the reason I'm starting with these pictures because these people may be the first climate change refugees. This is a picture of what happened after a relatively recent king tide, and they live on atolls, have lived there for several hundred years, and lately at the high tides in the spring, the king tides, their islands have been inundated, and the first thing that goes when that happens is the drinking water. And here's a picture of them relocating to a larger neighboring island. Okay, now global sea level, as you probably all know, has been going up, and just about everywhere. And if you look at this picture, you will see that in the Western Pacific, including the Carteret Islands, it's been going up about 3 times faster than the global mean. It's also, by the way, not going up or maybe going down a little bit in the Eastern Equatorial Pacific. So there's a rise in sea level in the Western tropics and tropical Pacific and a fall in the Eastern tropical Pacific. This is obviously not a simple thermal expansion of the waters or simply adding water from glacial melt. It's a dynamical effect that is related to other changes in the ocean and atmosphere. Okay. Now, you might ask, since I've seemed to have switched gears, what this has to do with the droughts in California and so on, and the other things that I mentioned. And one of the things I will try to do now is tie all these things together. Okay, let's start with a hiatus. Okay, there has been a slowing in the rate of global warming. In fact, it kind of stopped over the first decade of the 21st century, and the question is why. Okay, and there are various ideas, more volcanic, or poor account of volcanic aerosol, solar variation, and so on. And one of the things one can note about this period is that it is a period where there's been an absence of strong El Nino events and an occurrence of strongish La Nina events. Now, just to, okay, so that's in this period. In the preceding period, this big peak that goes up was the 1997-98 El Nino, which is one of the larger events of the last probably 400 years. Okay, just to say a word about El Nino and its associated atmospheric change, the Southern Oscillation, which becomes, I hope, relevant later. This is a picture of the sea surface temperature anomalies, the departures from normal in the 1997-98 El Nino, and you can see that there's a very large warming in the Eastern Equatorial Pacific and a bit of a cooling in the Western Pacific, kind of the opposite of the sorts of changes in sea level that I was pointing at earlier. And those kind of changes in sea level would be associated with this change in sea surface temperature. El Nino is pretty famous by now, and it is understood, we think, and the understanding is this, that it's a coupled behavior coupled between the ocean and the atmosphere. If the sea surface temperature now I should really have this thing working. Ah, good, okay. In the normal state, what's the usual state, I should say, the Eastern Equatorial Pacific is cold relative to the west. The temperatures here can be like 30 degrees Celsius, so that's 29, 30, so that's in the high 80s. Very comfortable to swim in if you like warm water. And over here it might be as cold as 20 degrees Celsius. I got an email from a park ranger I know on the Galapagos. It's 19 degrees C, so that's about 66. Some people don't like my wife, wouldn't go into that water at that temperature. Okay, so it's a big difference. And it's associated with the trade winds because the temperature difference makes a pressure difference, makes the winds blow this way, and the winds blowing this way also are responsible for the temperature difference. I'm not going to go into things in detail, but El Nino, this state, and in its extreme form it's called the La Nina state or a cold state, is the opposite in this sense of a state in which the anomalous flow in the atmosphere is from west to east, and the temperatures warm up in the eastern equatorial Pacific, and sea level rises over here and drops over there. In this state, sea level is higher over here and lower over there, as in that picture I showed you of the trend over the last few years. Now, a lot of the things that go along with this change, okay, are El Nino is a phenomenon with a time scale of 2 to 4, 7 years, but a lot of the things that go along with this change will occur with the same kind of temperature pattern in the ocean over almost any time scale, because the changes that matter, let's say changes over North America, are changes in the atmosphere, and the atmosphere reacts quickly to what's going on, quickly being a few months perhaps, and if it continues for a long time, the atmospheric response tends to continue for a long time. It's not a perfect rule, but it's a good rule of thumb. Okay, now, okay, this is terribly washed out, which is too bad, okay, since I can't see the contrast. Okay, we'll have to do this, redo this picture in stronger colors. But if I look at the trends in sea surface temperature between 1979 and 2005, the observed trend was such that you had warming out here where the yellow you can see is, and virtually no change over there. If you look at the ensemble of model means, if you look at the ensemble of the simulations from the models used in the last IPCC report, AR5, called CMIP5 ensemble, what you can't see here, but I can see on the screen a bit better, is that they tend to warm over here more than they warm over there. So it's the opposite pattern, okay? So while the observed is cool, the models are not cool, okay? Now, it's a relatively small difference, and all the reasons why this happens, I can't take the time to go into. Just another way of saying there's not real agreement on it, so you talk for a long time and don't reach a conclusion. But I want to point out that this pattern in the observations is the negative phase of what is called the Pacific Decadal Oscillation, PDO, and the pattern in the bottom, which again you can't see, but you'll see more clearly, I hope, in some later charts, is a positive PDO. So it's not exactly that pattern, but it's close to that pattern. It has some of the more important characteristics insofar as the way the ocean influences the rest of the world. And it makes a difference whether you're in the positive phase or the negative phase. In general, these patterns that have names like Pacific Decadal Oscillation, this one actually has several names. But in general, if people have bothered to give them a name and the name is stuck, there's probably a reason. And this does have some important consequences, a few of which we'll touch on. It's also very important in our business to have a 3-letter acronym. Okay. Now, if I look at, again, it's a similar sort of picture of the trends in in air temperature, surface air temperature over the Pacific. Again, this is just for this period of the hiatus now, but you have the same kind of thing. It's cold or cooler in the in the eastern equatorial Pacific and warmer in the western equatorial Pacific. And there's a sea level pressure pattern which over this period, the trend is in the sense of a stronger pressure gradient in the direction which would strengthen the winds which blow from east to west, strengthen the trade winds, and that's the kind of thing you'd expect. You might have guessed if you only knew that the sea level slope had gone up over the period, which was what I showed in that sea level slide. So all of these things are fitting together well. Now, I'm going to talk about, for a moment, about a simulation done, reported in a paper by Kosaka and Shia, which is a very nice study. They took the GFDL model, okay, and just specified the temperatures in that turquoise, okay, there we go, in this box, okay, where it's cold. They forced they used a coupled model, but they forced it to stay cold in that box, okay? And then what they found was that it reproduced many of the features in the observations, in particular the rest of the pattern of the ocean warming and a few of the other features, including the warming in the southern hemisphere and a fairly similar sea level pattern. But most important for present discussion, okay, they were able to show the following. If the black line is the observed global temperature, okay, so you're looking at global temperatures from 1950 onward, and that's the black line. If you run the models like the CMIP models I showed for this period, putting in volcanic aerosol and some other things, okay, you tend to get this blue-purple line here. And this difference, the fact that the observed temperatures leveled off is the hiatus, and the fact that the expectation, the main expectation based on the model is that the temperatures would increase, that global warming would continue unabated is reflected in this purple. Purple curve. So, okay. And now this is actually not a very big deal in terms of the size of the temperature anomaly, but it caused a lot of political fuss, okay? And so that kind of turned it into a big deal. And I suppose in another sense, the one interesting kind of question is, well, what happened to make this happen and how come the models don't do it better, okay? Or could we say they don't do it at all? I don't think we can quite say that, but we might ask why they didn't do it any more often than they did. But in any case, what the Kosaka and Shia showed was that if you simply keep the eastern equatorial Pacific temperatures cold, and you look at the global temperature that results in that simulation, then it comes into rather close agreement with the observed, okay? So the implication is that whatever changed the temperature in that region was enough to account for this hiatus in global warming, and the leading idea for what would have changed that would be natural variability. Now, on one level, it shouldn't be terribly surprising that controlling the eastern equatorial Pacific temperatures would lead to a control on global temperature, because if you simply plot the temperature in a box in the eastern equatorial Pacific, it's a standard box that people in our business use called Niño 3. It's smaller than the area that they actually changed. And if I plot that scatter plot against global temperature on the y-axis, Niño 3 on the x-axis, if I take all points, I get this curve. If I take the period of this decadal changes, I get this. There aren't so many points, but in general, there's a pretty decent relationship between the two, okay? And people know this, that in an El Nino year, the global temperatures tend to go up. In a La Nina year, they don't go up, okay? And it holds over a variety of timescales. If I now look at the global temperatures again, and I look back in time, you can see where the green bars are, that the hiatus that we've had now is nothing new. These kind of things have happened throughout the record, and in particular, in the 40s into the 50s, there was a long one, and at the time, actually, getting into the 50s and 60s, there were a lot of people who were saying, it's cold, it's getting cold, because you can see there's a slight downward slope, things were getting colder, and they were calling for the return of the ice ages, okay? You've probably noticed, well, maybe not today, but on many days you've probably noticed this hasn't happened, okay? People in Buffalo may be feeling differently. Okay, so this has happened before, and if I take an index of this PDO, which again, cold means it's colder in the eastern equatorial Pacific, warm means it's warmer, and I kind of line it up in time by, I didn't make this picture, and in fact, I can't even, there are several PDO indices, and I couldn't tell you exactly which one this is. For this purpose, it won't matter. But you can see that there's a kind of correspondence between the cold phases of the PDO and the pauses in warming. And there aren't enough of these things. If you're a stickler for statistical significance, you're out of luck, okay? Because there's nothing you can do with so few events. Okay, so in other words, what I'm doing so far is presenting evidence that the hiatus is highly likely to be a consequence of the changes in the Pacific, and the changes in the Pacific are probably, we'll start with this, probably internal variability. And later Alan Roebuck will probably want to make a case for volcanoes. Because that's what he does. It's good. Okay. All right. Now, let's go back to last winter, which many of you probably do not want to do. I myself tried to spend the winter in Miami, but I did come back and wade through the snow for a while. Anyway, last winter, if you look at the temperatures, it was warm in the west, cold in the east. I don't think anyone who was here then doesn't have to be convinced of that. And it was also dry in California and the Southwest, a drought that has, of course, continued and, in fact, started around after the 1997-98 El Nino. And it's continued with little bit of, some years are better, some are worse, but basically they've been in drought for most of those 15 years, okay? And this was attributed in an immediate sense to, well, okay, so first of all, here is the cold air, the surface temperature pattern, again, over a larger swath, and it's related to the jet stream here. It was cold over most of Canada. It was warm over Alaska, record warmth for much of that winter. Now, at the same time this was going on, there was a tremendous amount of rain in Britain, okay? The dark blue curves are 200% of normal, okay? I mean, this is a place where it rains a lot, so to rain twice as much as normal is a lot, okay? And some of the pictures I have are from a UK, United Kingdom Met Office report because they actually had to talk to the public about why is this happening, okay? Now, all of these wiggles and the consequences were attributed in the media to the polar vortex, okay? And I know that this somehow got through to people because my 7-year-old granddaughter started talking to me about the polar vortex, and they don't even have television. I don't know where she got this from, so it clearly had diffused through the population pretty far. We used to call this the jet stream, but anyway. Okay, now, again, let's go back to an analog with El Nino and La Nina, okay? And the top is the El Nino picture, the bottom is the La Nina picture, but let's focus on the La Nina picture because that's the more relevant one. And what tends to happen in the La Nina year is that the pressure in the vicinity of the Aleutian low becomes higher than normal, and you have a deflection of the jet stream over the pole, like this. So it carries warmer air up into Alaska and then colder air down over the middle of the country. In a typical El Nino, it can be variable, and you can get that other path shown in something like orange. But the other consequence of this is that storms track further north than usual over North America, and so it tends to stay drier in the southwestern US and in California, and that's consistent with, crudely with the patterns we have. It's not to make a total attribution, but basically this kind of pattern in the jet stream is the sort of thing that does tend to go with warm and dry in the west and southwest, and colder over much of the center and eastern part of the country. Okay. And indeed, this, as I said, the southwestern US and northern Mexico have been dry for a long time. This is from 2004, and what's shown is Lake Powell, which is a reservoir, and that white ring you see, that's the bathtub ring, okay? You can get a sense of scale from the boat. And there are very long docks now extending from where they used to be to where they are now, okay? Now, an interesting thing is that this kind of drought, see, I want to look at this to see how well you can see it. Okay, so this is the precipitation anomaly observed in the upper left of essentially the shortfall in rainfall during the period we know as the Dust Bowl, okay? It's more complicated than what I'm going to talk about. In particular, I'm leaving out the dust, which makes a difference, okay? But if you run a model forced by the sea surface temperature pattern, this shows the anomalies in the sea surface temperature for this period 32 to 39 here. The anomalies get up mostly to a couple of tenths of a degree at most, okay? So they're not big, okay? And yet a model an atmospheric model, which the only reason it knows that these years are different from the climatological average is these sea surface temperature anomalies, these few tenths of a degree. They have a particular pattern, which I'll come to in a second. And that pattern is enough, apparently, to give you the picture on the top right, which shows that the model does a pretty decent job of capturing many of the features of the Dust Bowl drought, okay? You can do even better if you throw in the dust. Okay? And the other thing to say is, if instead of using all of the global temperature changes, you simply feed this model the tropical Pacific, the region between those magenta lines, okay, then it's still able to capture drought. It's not quite as good as this drought, but it gets most of the, it gets the idea again that the major drought, there'll be a major drought over the US and so on. The model is systematically too far to the south. That's not a problem about the SSTs. It's a model bias. But the point is that clearly this region has a powerful influence on the precipitation patterns over North America, and the other region which does matter is the Atlantic, which you can see is the North Atlantic at this time was almost uniformly warm, and that also matters for this drought. But that's essentially the feature in the whole global sea surface temperature pattern that you need to get the difference between that picture and that picture. Okay, so the point here is that it is this pattern, and it goes with those shifts in the jet stream, which is responsible for the kind of weather patterns we had last winter, and more importantly, the drought in the west and southwest that's persisted through this whole hiatus period. Okay, this is work done earlier. This work, by the way, is done by my colleague Richard Seeger, who's really one of the experts on drought now, hydroclimate in the world. Okay, and again, this is for just the earliest part of this drought, 1998 to 2004. And now, if you look at the sea surface temperature pattern, it's all red because this is relative. An anomaly is a change from normal, and what you define as normal matters. And this, in this case, what was taken as normal is the mean temperatures from 1856 to the present, or to 2000 actually. And relative to that, the whole world has warmed up. Okay, you probably all know that. Okay, but you can see that during this period, the eastern equatorial Pacific did not warm up relative to that. It was colder than normal. Okay, so again, we have this pattern of relatively colder in the eastern equatorial Pacific, warmer in the western equatorial Pacific, and that, again, if you run the model with just the temperature pattern, you reproduce a good bit of the observed drought. You need the rest of the world, you do a little bit better. Well, maybe it's a little bit better, maybe it's no better. Okay, so again, the consequence, the point I want to make is that having this deflection in the jet stream makes a difference in where it gets warm and cold and where it rains. Okay, and this deflection in the jet stream, at least in some cases, we clearly can associate with the changes in the tropical Pacific temperatures. Now, if this is the same picture I showed before, all I did was change the label from surface air temperature to jet stream because I want to emphasize that, again, you have this flow of air goes up this way toward Alaska, comes down. Okay, it was really cold in Alabama last winter, and then goes back up again, headed toward England. Okay, this is from January 2014. Right, and here is a picture then of the sea surface temperature anomalies from a year ago. And again, this pattern where it's warmer in the west, colder in the east, in the tropics. And if you look at the airflow that goes with that, okay, and start in that yellow region, okay, what you see, I did this that one by hand. The little bumps are probably are not realistic. Okay. In the old days, we used to get to color in view graphs. You know, it was more therapeutic than doing it on a computer. But anyway, the path of this flow, and this is in the observed, I'm going to show you in a minute, but I want to show you this first because it's the cartoon is easier to see, is like this. Okay, it's over North America and into Europe. It's the same sort of path that I was showing before, and people, in particular the UK Met Office people in their report, traced the origins of this back to that region of warmth in the western tropical Pacific. It's not surprising in a way. There's, I mean, it's well known that that is a genesis region for a lot of circulation changes. Okay. Here is a picture which is a little harder to see, but it's actual data of the 850 millibar hectopascal winds, so a lowish level in the atmosphere, but above the boundary layer that we live in. But it again is showing you that the jet stream is headed north toward Alaska, then comes down over the U.S. The yellow circle emphasizes that, and then it goes across. So this is 2014, and it's again I'm just sort of emphasizing the same pattern. And what the British were concerned with is the fact that it continues strongly from this position over which is circled in red, where the airstream picks up a lot of moisture and warmth and then heads over toward Britain. And they attribute the unusual rainfall to that. And again, here's the cartoon version, which might be easier to see. Okay? So, okay. So far what do we have? I am associating at least the hiatus, the unusual weather over North America, including the droughts and the temperature patterns, and the rainfall in Britain with these anomalies in the tropical Pacific, which are probably but not certainly a consequence of internal variability. It is at least the kind of internal variability where it is a pattern that has appeared in the past at times when I won't say there was no anthropogenic influence on the atmosphere, because there was some CO2, and there were even stronger doses of industrial aerosol. But in any case, this seems like a pattern that has recurred not just over this period, but even further in the distant past based on paleoproxy data. A final thing to point out is over the first decade of the 21st century, much of that time, there's been a severe drought in East Africa until Syria and Syrian refugees pushed it out of first place. The largest refugee camp in the world was in Kenya, primarily Somalis fleeing a country that was in severe drought, and so things wouldn't grow, and because of the complete breakdown of any polity, there was no possibility of bringing aid in, okay? And this is a particularly interesting case, well, first of all, because it is a humanitarian crisis, but also the projection, the global warming projections from IPCC models are that this is an area that is to become wetter with an increase in CO2. And that is, well, okay, that's the projection. Now, droughts in East Africa are also related to La Nina kind of SST patterns, okay? In Kenya, there are two rainy seasons. There's one in the fall called the boreal fall called the short rains, and one in the spring, the long rains, okay? And most of the variability historically has been in the short rains, and it has been associated with El Nino events, or the El Nino Southern Oscillation ENSO cycle. So the droughts would be La Nina years. However, in the last decade, the spring rains have also been strongly reduced. And that is something that people hadn't noticed before, although it's happened probably it certainly happened in the past, but it's one of the difficulties there is you don't have a very long data series that you could feel is reliable of rainfall, okay? And it turns out there's a more like a negative PDO pattern, I said La Nina-like, but more, they're similar, okay? And there's very recent work by my neighbor Brad Lyon and others suggesting, or really, I think, making a good case that this rainfall is, again, related to temperature changes in the western tropical and subtropical Pacific. Okay. So, the model, is this natural or the model's just wrong? Okay. The question might be, is there something about that pattern that's associated with anthropogenic influences on the atmosphere, or is it just some natural swing of the PDO? I can't give you a definitive answer to that. The prevailing wisdom would be that it's natural. I'll come back to that again. Okay. The models are certainly in many aspects wrong because almost all of these models are, for example, unable to produce the correct climatology in this region. Models are actually good at a lot of things, but there are a few places where they're, let's say, not so good. And this is one of the more, places where I'd say the models are least suited to be relied on. Okay. So the models are certainly wrong, but it also may be natural. The idea if it's natural would be, well, the model is actually right about what global warming will do, but we're not seeing that yet. Okay. It's been so far masked by the natural internal variability in the climate system. Okay. And the climate of now, of this decade and of the next decade and so on, an important point to keep in mind in terms of vulnerability to what's in the tropics and anywhere, in fact, to what will happen is it will be a mixture of a forced signal due to human interference in the climate system and internal variations that have gone on, if not forever, for quite a long time in this climate system. Okay, conclusions. Okay, so, the droughts in California and the Southwest and all those other things over the U.S. from last winter and maybe what's going on now are due to variations in the jet stream, okay? And the same is true for the heavy rains and flooding and coastal damage in Britain, okay? These things are influenced to a substantial extent by temperature patterns in the Pacific, in particular this pattern of being warmer than usual in the western Pacific, which we might think of as either La Nina-like, an uncertain phrase, or a negative PDO, okay? But there's probably something more going on, and one of them is it could be just random bad luck. Another idea might be that it has to do with the configuration of the stratosphere, something called the polar night jet, which is in turn could be related to the stratospheric tropical cube quasi-biennial oscillation. That's for further research, let's say. Or, in my opinion, it might be that we're not really taking proper account of climate change in this thinking, okay? It's also the likely cause, the negative PDO phase is the likely cause of the hiatus and all the political theater, therefore, that went with it. And it's the probable cause, I think, of the drought in East Africa. We presume this is an internal mode of variability, and then perhaps you could say it was an IPCC sort of shooting oneself in the foot not to make more noise about the possibilities of internal variability when they projected the future. But anyway, I'm not so sure that's true. I think it could be more anthropogenic interference. But in any case, models do not always get it. And so far, they tend to predict the opposite for the future, but they also have tended to make changes over the 20th century, particularly the end of the 20th century, that are, that their average changes are more or less the opposite of what's been observed. Okay, thank you.
Thank you, Mark. We have time for questions, and it is a tradition here at Rutgers to allow the graduate students or the students to have first crack at the questioning. We've provided a microphone up here at the front so that all may hear the question and that we could get you on television as well. So line up at the microphone, and if a student is behind you, you are to give them preference.
Okay.
You want students to
Okay. I'm a student my whole life, so.
Well, somebody's got to.
Mark, one of the fundamental, I'm Alan Roebuck from Environmental Sciences. Mark and I went to grad school together. So. One of the fundamental questions that you brought up is the relationship between natural internal variability and things that are forced by global warming, by human changes.
Yeah.
And as I understand it, the PDO is a cycle. Well, it's not a cycle because I learned in my statistics course that you need at least 6 of them to call it a cycle. But it's an index that has a linear trend taken out. Is that right?
I don't know if that was done there, but it would. Yeah, I mean that would be a good idea given the secular warming.
If you put the linear trend back in and put the forcing in, doesn't it sort of go parallel to the global average temperature change? And so I'm just wondering if some of those periods are forced by not just volcanic eruptions, but tropospheric aerosols and other causes of climate change. And sort of a related question is there a fundamental physical mechanism that we understand for the variation of the Pacific that has this time series that is well understood and well represented in models?
Okay, those are all good questions. I wonder myself. Okay, so let me do it this way. There have been, over the 20th century, there were quite substantial variations in the aerosol load in the atmosphere, both because of changes in volcanic eruptions and because of human activity and things like world wars. And I'm very open to the idea that this mode of variability might be forced by such things. Now, this is not. A lot of the discussion of forcing and that internal has been designed to try to make a case for attribution and detection and attribution of climate change. When you do that, you're looking for patterns of changes that are least like anything natural, okay? But in any system that has natural modes, you expect, if you force it, you might see those natural modes amplified or suppressed or something, but they don't go away, okay? And the forcing can actually bring them out and stimulate them, okay? So I think that's a real possibility for what's happened here. In political terms, I'll say this, there's a tendency in our field for people to sort of say, to use the kind of scientific standard of if we don't know, okay, if we can't say we're 95% sure of it being attributable to human interference, then we insist it's not, okay, or we can't show it is, okay. And that's one way of doing things that makes sense in a lot of scientific contexts. In this context, it might just as well be able to say, well, we don't know, it isn't that, okay? And from a risk assessment standpoint, you don't wait until you're 95% certain of something to take action. So if you take a risk assessment standpoint, you might say there's a good chance this is due to something that we're doing to the climate system. The next question Alan asked, or one of the questions Alan asked was, well, do we have any, is there a good theory for this time scale? And the answer is no, okay. There are a number of ideas about how it might go, which is, if you say there are many ideas, it's like saying, well, we don't exactly know. I personally think that it's pretty much the same kind of, and I won't go through what they are, but the same kind of couple dynamics as gives you the shorter time scale of ENSO. And there are ways that it gets transmitted, in particular to the extratropical North Pacific, that are, I think, pretty well understood and have been, studied. But exactly what determines that time scale, I don't think is an answered question. Just as I don't think a lot of the Atlantic variability is really understood, despite a tremendous amount of attention and a lot of good work by, in particular, colleagues at GFDL.
Quick question about data that might influence some of the things you're talking about. I read a book called Thin Ice, I believe it was called, about Lonnie Thompson doing a lot of cores, ice cores, and some of those would have been in East Africa. Would an ice core show the rain variability within a year, or would that just show data for time periods greater than a year? You mentioned that you didn't have data about the variability of rainfall over a long period of time. That's why I asked the question.
Yeah. I suppose you could try that. You could try that because an ice core does let you get at accumulation rates, maybe. So there might be something there, but it would be a little, imprecise. And the other difficulty, this particular, in addition to the lack of data, it's a rather complicated region because you have the Ethiopian highlands, the East African highlands, in between this thing called the Turkana Channel, which is particularly important because it's the site of a lot of the digs that have dug up our ancestors. And so there are lakes and so on. So it's in other words, even getting that one point well would still allow those who are finicky about data, properly finicky in this case, I would say, to say, well, that's not really representative.
Hello. In one of your slides, which had more long-range data, there was a blue band off the coast of northern Chile with a tight band in latitude, and it was blue. It was a remarkable, defined blue band. And in a more recent piece of data, that blue band off the coast of Chile was broader. And it suggested that there was a remarkable upwelling in the steepness of the shape of the upwelling of the northern path of the cold current up off Chile. Is there any correlation between that data and what you know about the upwelling?
I'm not sure this is going to be
It was way back at this.
beginning.
Okay.
All right, well,
You have to go back about 20 slides, I think.
we can attempt that, I guess. What?
When you find the slide, is this a slide?
No, I guess go back. I think
Okay.
I'm not sure what is. Do you know which? That one?
Was it that one?
Well, that's the one that's broader.
Okay. Okay, I don't think.
And prior to that, you had data from
Yeah.
in the 30s up till recently.
No, that's okay. Just stay with that one.
Save that one.
Back.
Stay with them.
Yeah. Okay. I think that's too far out, to attribute to coastal upwelling alone. I would say,
But
that's an anomaly that's probably wind forced over much of the ocean. So this is it's not normal.
Okay. But this tight blue band on this chart, previous
That's more
chart.
normal. You know, that there's a coastal upwelling zone there, and that would be the normal condition, but
I see.
this is a departure, yeah.
From that.
Yeah. Up. Okay.
Thank you. My name is Petra Chaka at Penn State. I'm going to be a little provocative here. You said controlling the temperature in the eastern equatorial Pacific allows us to explain or understand the hiatus. You didn't suggest the following, but let me push it that far. What if people who are interested in geoengineering better understood the message you gave us, saying, what if you could just control that window that you showed us in the model, and if we could control the temperature in the eastern equatorial Pacific, could we control climate change?
No. Okay. Well, first of all, Alan has written rather eloquently about some of the dangers of geoengineering, but let's just say it's not that simple because, you know, if you take the geoengineering to the level of you wave your magic wand and everything is fine, then yes. But if you look at schemes like for you know, controlling solar radiation rather than the idea, let's say, I mean, geoengineering, for example, includes you know, sucking the CO2 out of the air. If you suck the CO2 out of the air and you did it, you would presume that would be good, okay? That's not on the immediate horizon, I would say, having, okay. If you're going to do this by putting, to use the technical term, schmutz into the upper atmosphere, okay, then you don't undo what having CO2 does, and you know, there's a fair amount of work on this, including, in my case, they did some explorations of paleoclimate cases, and so it won't undo what global warming does. In particular, it has a different impact on rainfall, okay? And rainfall is probably more important than temperature. The second thing is that on one level, we don't completely understand what happened to the heat that isn't on the surface during the hiatus. The leading idea is that it went into the ocean, okay? That might be right. Turns out, though, that the uncertainty in our knowledge of the top of the atmosphere radiation balance is great enough so that if you wanted to say, my hypothesis is it all went out the top, you couldn't say, you couldn't from the data show that that's wrong. And the analysis of the heat going into the ocean, you know, that there's been more heat going in lately, that's also, in my opinion, and this is a technical issue which other people would have different opinions about, I think, but I'm right and they're wrong, of course, that you couldn't tell from that either, that really more heat did go into the ocean. You want to take on geoengineering for a
No,
few-
I just wanted to ask a different question. This figure, all that red at the top, shows a very warm Arctic Ocean. And one of our colleagues here, Jennifer Francis, I don't know if she's here, has
Yeah.
hypothesized that all the things you were talking about might be controlled from the warming Arctic rather than from the tropics. And I was just wondering if you had any thoughts about that.
Yeah, I don't, okay. You know, being a provocative hypothesis, there were a lot of questions raised and some, you know, I'd say that there's been some good work which casts some doubt on whether the inference made from the data is correct. I wouldn't completely dismiss the hypothesis, and one way in which I think it's been sort of revived is in the notion that the state of the polar night jet, which is essentially the Arctic stratosphere, matters for a way a lot of these things play out, okay? And so that would be a way in which, you know, now what that has to do with the surface changes in the Arctic is, I think, a pretty open question. So I think that work, Jennifer's work, raises some good questions, and let's say, as is not uncommon in our business, doesn't answer them to everyone's full satisfaction. And I'm not ready to buy the way that argument was made, but I think there's a good possibility that all this warming matters. One of the things again is that if people look at models and they look at what the models do with the warming Arctic, it's not consistent. Basically, the jet in the models, the jet more tends to weaken, and so instead of getting these stronger oscillations, it kind of goes kind of blah. Okay, and that's possible. Okay, there's other work. Just now sorry, maybe I should stop, but I mean, okay, there's other work that, for example, Tim Palmer has done and others have done, showing that, if you just go to a much higher resolution than the climate models, you get a different climatology even. You get a different distribution of what we call blocking events, these persistent things, and of the tendency to get these kind of waves. So it may be that the inference made from the models in this case is also wrong, and that if we did this with something more like the weather prediction models, that kind of resolution, you'd come to a different conclusion. Okay.
Hi, Mark. I'm a PhD student in Earth and Planetary Sciences, and I'm actually working on sedimentary records from the Turkana Basin. So coming from that standpoint, you made a very compelling argument that the models for East Africa right now have a great deal of uncertainty. And so I'm curious what kind of, from the physical boots on the ground side of things, what sort of information could we as geologists provide to the modeling community that might help resolve some of that uncertainty?
Probably nothing. Unless you can find rainfall records, which you might be able to do actually, because often in places, going out there are people on farms and so on who may have kept records that nobody knows about. That happens actually, so that would be valuable. But I think I'm very interested in a lot of the questions about. In particular, the aridification of East Africa during the Pliocene. And, one of, actually I'm going to go back, I hope, to working on that based on, what is actually the more recent work on modern climate, suggesting other ways perhaps of getting this to work than my first try at it, which didn't work.
Hi, Professor. My name is Paul Franco. I have a question of a non-technical nature. And you mentioned earlier that there's about a 95% certainty, but that difference between the 95 and 100% certainty is what drives the whole political discourse about the perils of global warming. What can the scientific community do as a unified forum to bridge that gap, to really educate the people at large, especially people in a position to do something about it, like government and industry, or to prevent from doing things that damage the environment in a way that's credible? Because as of right now, there's a large segment of the population who still believes that this is either a hoax or it's politically driven. And I tend to disagree with that.
Okay, so here I'm asked a question on which I am certified non-expert about, what you can do to change people's minds. And two things, let me take this from two different examples, okay? The first is what goes on. There's a fossil fuel industry. It has an enormous investment in fossil fuels. It has a lot of money. It spent that money to corrupt the political process and to spread misinformation. And the way they have done it, it's pretty well documented, for example, in the book by Naomi Oreskes, that they've done it in exactly the same way that tobacco companies obfuscated the fact that smoking causes cancer. And not only have they done it the same way, it's been done to a good extent by the same people. And then to my horror, I discovered I know a lot of those people. Okay, but that's off the point. Okay, so there's that. Okay, and that's tough. And you know, one of the things is that in order to change and get away from fossil fuels requires a cycle of innovation, and that's there's a lot known about innovation, but it's also not what your standard economists tend to talk about. So when they do evaluations of what it's going to cost to make a transition, okay, it usually doesn't factor in, or it almost never factors in fact, what the gains might be from an innovation that would change our infrastructure to depend on renewable resources. It's all about what it's going to cost, okay, which I think is basically historically wrong. Okay. So, and the reason that's important is I don't think you change people's minds. I don't think that the facts are not terribly important, okay. It's not about the facts. The best predictor of people's opinions on global warming is political affiliation. Okay. Not college education, not how much they read about this, but political affiliation. And you know, that you're not going to get at that by changing the facts. So addressing the facts is a waste of time, I think. So it's not us scientists like me. I mean, I can talk about it because I'm a citizen. But in my role as a scientist, most of which I have to say, I frankly don't think is going to make a damn bit of difference. Now, on the good side, you know, if you look at some of the issues in this country, like same-sex marriage, okay, you know, there was tremendous opposition, okay, and somehow it seems as though it almost crumbled overnight and things turned around. And I think the same thing will happen here. There'll come some point and it'll tip. It probably will take some climate-related catastrophe and while we are busy arguing about whether this is or is not attributable to global warming, if enough people believe it is, okay, that'll make the difference, okay? At which point it might be that if we're going to say we don't think it's attributable to global warming, we should consider whether we have a moral responsibility to just shut up. Okay, now, you know, this is just my opinion as a citizen, so you can take it for what it's worth.
Thank you, Mark. No, don't worry about it.